The dwarf planet Pluto, situated at the farthest reaches of our solar system, is enveloped by hundreds of thousands of icy celestial bodies and asteroids within the Kuiper Belt, a vast region of space beyond Neptune. Once revered as the ninth planet, Pluto derives its name from the Roman god of the underworld. However, in a pivotal moment in astronomical history in 2006, Pluto was officially downgraded from its planetary status, reflecting the evolving understanding of our cosmic neighborhood. Our current comprehension of the solar system delineates a tapestry of celestial entities, numerous asteroids, a select group of dwarf planets, and a count of just 8 classical planets. Throughout the annals of human curiosity spanning centuries of astronomical observation and exploration, our understanding of these cosmic bodies has burgeoned significantly. We've gained insights into their compositions, behaviors, and potential habitability, painting a more nuanced picture of our cosmic surroundings. Yet amid our growing knowledge, the magnetic allure of our own galaxy continues to beckon exploration and discovery. The James Webb Space Telescope, a pinnacle of modern astronomical technology, stands poised to unravel some of these lingering mysteries, including those surrounding Pluto. Despite its diminutive size and eccentric orbit, Pluto held a special place in the hearts of many for 76 years, boasting the distinction of being the smallest moon-bearing object in our solar system. Pluto's reclassification ignited a fervent response from the public, underscoring the emotional attachment people felt toward this distant celestial body. However, scientific rigor dictated that for an object to merit planetary status, it must adhere to 3 key criteria: orbiting the Sun, possessing sufficient mass to assume a nearly round shape under its own gravity, and clearing its orbital path of debris, criteria that Pluto, with its lopsided orbital path, ultimately failed to meet. The term planet has undergone a fascinating evolution over the course of astronomical history. Initially, it encompassed any substantial celestial body observed in the heavens, including moons and asteroids. Pluto's discovery in 1930 by American astronomer Clyde Tombaugh stirred global excitement, only to be followed by revelations of similarly sized objects within its vicinity, casting doubt on its planetary stature. Amidst the ensuing debate, Professor Mike Brown's groundbreaking discovery of Eris, a Kuiper Belt object comparable in size to Pluto, further muddied the waters, challenging the traditional definition of a planet. This prompted a robust discourse within the astronomical community, ultimately leading to Pluto's reclassification as a dwarf planet during the International Astronomical Union (IU) conference in Prague in 2006. Thus, Pluto's transition from planetary prominence to dwarf planet designation serves as a poignant reminder of the dynamic nature of scientific understanding and the perpetual quest for clarity amid the vast expanse of the cosmos. It underscores the intricate interplay between observation, theory, and consensus building that defines the pursuit of knowledge in astronomy. After extensive discussion, a revised definition of a planet was proposed and put to a vote during the August meeting of the IAU, the authoritative body responsible for naming celestial objects and defining astronomical terms. In this meeting, the scientific community grappled with the need to clarify the classification of celestial bodies, particularly those in the outer reaches of our solar system. Following deliberations, dwarf planet status was conferred upon both Pluto and Eris. This decision was significant as it marked a departure from the traditional understanding of what constitutes a planet and reflected a more nuanced understanding of celestial dynamics. Eris, previously known as 2003 UB313, was renamed after the Greek goddess of strife, reflecting the controversy and debate surrounding its classification. Mike Brown, a planetary scientist at Caltech whose work contributed to the reclassification of Pluto, gained widespread recognition for his role in the process. As a playful nod to his involvement, Brown earned the affectionate moniker, Pluto Killer, on Twitter. The revised classification prompted the immediate reproduction and updating of educational materials, including posters and textbooks, to reflect the new understanding of Pluto and Eris as dwarf planets. However, not all members of the scientific community readily embraced the IU's definition of a planet. Some planetary scientists, particularly those with a focus on Pluto and similar objects, expressed reservations about the new classification criteria. This divergence of opinion sparked ongoing debates within the field of astronomy regarding the precise criteria for classifying celestial bodies. Scholars contributed to these debates through academic papers that examined historical precedents in scientific literature. They argued against the IU's definition of a planet, citing examples such as Ceres, which was initially classified as a planet upon its discovery in 1801, but later reclassified as an asteroid as more objects were discovered in the asteroid belt. The debate over the definition of a planet extended beyond scientific circles and into broader societal discussions. It raised questions about the nature of scientific classification and the implications of redefining long-standing astronomical terms. Some expressed concerns that a narrow definition of a planet could limit our understanding of the diversity of celestial objects in the universe. Despite these debates, scientific exploration continued unabated. In 2015, NASA's New Horizons spacecraft conducted a historic flyby of Pluto, providing unprecedented insights into this distant world. The mission revealed a dynamic and geologically active planetoid with features such as nitrogen cliffs and a prominent heart-shaped region, captivating the public's imagination. As we reflect on these developments, it becomes clear that our understanding of the solar system and its constituent bodies continues to evolve. The reclassification of Pluto and Eris as dwarf planets represents a milestone in our ongoing exploration of the cosmos, underscoring the complexity and diversity of worlds beyond Earth. As New Horizons journeyed through space at an astonishing speed of 32,300 miles per hour, it provided a unique opportunity to capture detailed images of Pluto's near side during its closest approach. However, due to the alignment of the spacecraft and the position of the Sun, the far side of Pluto, often referred to as the dark side, remained hidden from view during the flyby. Nevertheless, scientists meticulously analyzed images taken by the spacecraft days before its encounter to gain insights into this mysterious region. Despite the challenges posed by the limited resolution of these images, they offered an unprecedented level of detail, allowing scientists to discern surface features down to about 1 mile across. This level of clarity far exceeded previous observations, including those from the Hubble Space Telescope, which orbits Earth. The analysis of these images has yielded fresh perspectives on Pluto's dynamic nature. Scientists are now delving into the landscape to unravel mysteries, such as the potential existence of an ocean beneath the icy surface and the mechanisms driving surface processes. Some intriguing findings even hint at the possibility of Pluto's harsh environment supporting microbial life. However, alongside these new revelations come fresh mysteries. Recently discovered ice formations resembling skyscrapers orbit Pluto's far side, their origins shrouded in ambiguity. Richard Binzel, a planetary scientist involved in the New Horizons mission, aptly describes Pluto as the gift that keeps on giving, as it continues to surprise researchers with its complexity. Before the New Horizons mission, the most detailed images of Pluto came from the Hubble Space Telescope, revealing a world with distinct surface features. However, it was the New Horizons spacecraft that provided the first close-up views of Pluto's terrain, including the iconic heart-shaped feature and the vast frozen basin known as Sputnik Planitia. The discovery of Sputnik Planetia's peculiar alignment with Pluto's largest moon, Charon, raised intriguing questions about its formation. Some scientists speculate that the basin's creation may have involved a subterranean ocean rising to the surface, causing significant gravitational shifts. Further evidence supporting the presence of a subsurface ocean comes from the chaotic terrain on Pluto's far side. This patchwork of hills, fissures, and plains bears resemblance to features seen on other celestial bodies where subsurface oceans are suspected. While the resolution of images from Pluto's far side remains limited, scientists eagerly anticipate future missions for closer examination. The discovery of fractures and other geological anomalies fuels speculation about Pluto's early history and the potential role of its subsurface ocean in shaping its surface. These findings challenge our understanding of planetary formation and highlight the dynamic nature of distant worlds like Pluto. As New Horizons continued its journey, scientists speculated about the fate of Pluto's rocky core. Eventually, radioactive decay within the core would have generated sufficient heat to liquefy the surrounding ice. This process would have caused the ice to shrink as it melted, leading to surface ripples akin to the wrinkling of an apple stored in a fridge. If this scenario occurred, Pluto's surface should display signs of wrinkling and cracking in recent photographs. However, when New Horizons captured images of Pluto's far side, it primarily revealed fissures rather than widespread wrinkling. These fissures suggested that Pluto's ocean, once liquid, had partially frozen over time. Notably, a massive crack running the length of the near side, wrapping around the entire planet from pole to pole, resembled Earth's East African rift system. This rift, likely a result of the freezing and expansion of the ocean, indicated the ocean's rapid cooling upon exposure to the frigid surface. The age of the fissure indicated that the ocean began cooling almost instantaneously upon reaching the surface, potentially fostering conditions conducive to marine life. Additionally, the crimson color of the water, indicative of organic molecules, hinted at the presence of complex organic matter. Laboratory experiments have demonstrated that such molecules can form through radiation similar to solar wind or cosmic rays, suggesting a plausible scenario for their existence on Pluto. Furthermore, the detection of ammonia ice on Pluto's near side supports the notion that the dwarf planet may harbor rich organic compounds. While this doesn't imply the origin of life on Pluto, it does suggest the potential for life to survive if conditions were favorable. Measurements from Pluto's far side have not only aided in the search for life, but have also led to the discovery of intriguing geological features such as ice chunks resembling skyscrapers. These ridges, distributed evenly and rising sharply into the sky, present a major mystery. Spectral measurements indicate that they are composed of methane ice, forming a belt around the equator.